Okay guys, so we're going to go through our lesson for today. So we're starting with some more unit conversions, and these are with kind of some silly made up units, but we're going to do them the exact same way. So if you want, you can pause this and try this first one. Okay, so we're going to just go ahead and start writing. We have 57.2 thingamabobs. So I'm just going to use that as our abbreviation for thingamabobs. I just made it up. And we're told here that we have 23 what's it and one thingamabob. So our first thing is to write our units, and our what's it's go up top because we have to cancel our thingamabobs, one on top, one on bottom. And now we put in our number. So the thingamabobs, we have 1 per every 23 what's its. So if we put this in our calculator, 57.2 times 23, we should get 1315.6 what's it. We have to go back and double check we have the right number of sig figs. So this, oops, that's not what I meant to do. This number here has 3 significant figures, and then remember that our unit conversion is going to have infinite number. So that means our final answer will have 3 sig figs, so we can write that as 1320 what's it, and remember we have to put that 0 there, otherwise it's just 132 as opposed to 1320. Or you can write it with scientific notations. You could write 1.32 times 10 to the 3rd power, and then our unit of what's it. Okay, so here's another one. You can pause the video and try this one out. Okay, so now we're going dingle hoppers to who's its. So we're going to do 42.567 dingle hoppers. And again, we're going to put our dingle hopper on the bottom and our who's its on the top so that our dingle hoppers can cancel. And now I put our numbers in, and the 23.6 times 10 to the 9th goes here, and the 1 goes up here. And in this, you have to be careful when you're putting it into your calculator, because I think the yellow ones that we have in class have some issues. So you want to just make sure that you put this whole thing in parentheses at the bottom just in case. So you do 42.567, and remember we're dividing because it's on the bottom of our fraction, and then you'll do parentheses 23.6 times 10 to the 9th. And one thing you might notice is that on your calculator it will tell you 0.123456782. Okay, and notice that this is because our calculator only has that many digits to report it. So in this case, you're going to have to change how it tells you the information. You're going to have to make it tell you in scientific notation, because this only gives us the 1 unit, our 1 sig fig, and we want to have actually 5, because 42.567 has 5 sig figs, and then remember again our 23.6 has infinite numbers. So if we put this in scientific notation, it tells us actually more decimal places. So it's 1.8037 because we want 5 just like this one, and it's times 10 to the negative 9 who's its. So we just have to be careful when we plug that into our calculator. Okay, so we did this little game of name that number afterwards to show that numbers have names. So like this, we can call it a dozen for 12. 13 we can call a baker's dozen. This we call a million. This number we call pi. And this number, guess I'm hitting the wrong button. This number you might know, or you might not, that we call it I, but that is just really for math. We're not really using that. It's an imaginary number. We're not using that in chemistry. And then we have a number like this. So this number, you may not know what it is called, but we could count it out if we wanted to and say that it is 602 hexazillion. But this is actually a number that we use quite a lot in chemistry. So instead of writing it this way with all the huge zeros, we're going to write it in scientific notation. So that would be 6.022 because we're only going to write the significant numbers. Everything else after that is not significant. Oops. And then times 10, and we have to figure out what we have to put our decimal to. And it's going to be 23rd, but we can go 3, 6, 9, 12, 15, 18, 21, 22, 23. This is a number that we will need to remember because it is called the mole. We call this a mole. So 6.022 times 10 to the 23rd. It's called this because it is, well, it's also called Avogadro's number, which you might need to know that. This is a picture of Avogadro and the scientist who came up with this number. It is the number of particles or atoms in 12 grams of carbon-12. So I don't care about you memorizing that, but it's just telling us the number of atoms in a particular amount of a substance. And that's a really huge number because atoms are really, really small. So we can kind of get an idea of how big this number actually is. If we had a mole of jelly beans, 6.022 times 10 to the 23rd jelly beans, how big would it be? And it would actually be the size of the Earth. And then if we had a whole mole of donuts stacked one on top of each other, it would reach 200 billion times from Earth to the sun and back. So not just from the Earth to the sun and back of donuts stacked all the way there. It would do that 200 billion times. This is an astronomically huge number, but it's because atoms are so tiny, there are so ridiculously many of them in any amount of a substance. Okay, so we can kind of think about for a second, if we have 1 mole of carbon, it's going to have a different mass than 1 mole of hydrogen. And that's because, why? It's because this mole is just telling us how many atoms. It's kind of like saying, well, let's just replace that with a small number. What if we had 5 atoms of carbon and 5 atoms of hydrogen? Which one is going to have more of a mass? And we know that carbon will, because carbon itself has its own mass that's smaller than hydrogen. So it's kind of like the question of which weighs more, a pound of feathers or a pound of bricks. We can think about which weighs more, a mole of feathers or a mole of bricks. And in this case, our mole of bricks would weigh more because there's the same number of bricks and the same number of feathers, but bricks weigh more because they're heavier. So it's kind of backwards, I guess, from that feather and the weighing and the pound example. Okay, so in order to use this information, we have to use something called the molar mass. And this is the number, it's a number that has been calculated and measured and recorded for us, and it's the number of grams in 1 mole of an atom. So the unit that we are going to write, which is very important to remember, is grams per mole. And when we abbreviate mole, we just write MOL instead of MOLE. It saves us 1 letter. So we're going to use our handy-dandy periodic table to determine these. So if we're going to do the molar mass of oxygen, we just look at our periodic table and it says the mass of oxygen is 16.00. So that's telling us the unit is also grams per mole. That's telling us that in 16 grams of oxygen, there's 1 mole of atoms. So if you weigh out 16 grams of oxygen, that has 6.022 times 10 to the 23rd atoms in it. And then our xenon, we can look again, we can find it, and it's going to be 131.29 grams per mole. So in the case where it's just one atom like these two, it's just going to be the atomic mass. Where molar mass is different is when we come into examples of compounds, because we want to know how many moles of that molecule there are, not how many moles of carbon or how many moles of hydrogen. We want to know how many moles of CH4. So for these, they're pretty simple. All you do is you just add up all of the mass of all of the things. So carbon has 12.01, and then we have 4. So you can think about it either as we're multiplying 4 times our hydrogen, which is 1.01, or you can think about it that we're adding 1.01 4 times, 1 for each hydrogen. So if we do that one, it is going to be 16.05 grams per mole. And we still want to kind of consider sig figs here. In this case, we're adding two numbers together. So because of that, when we add or subtract, we're looking at the number of decimal places. So both of these go 2 after the decimal place. So our final answer will also go 2 after, which is what we have here. So they're pretty simple once you get the hang of them. So you can try a couple of these. So you can pause it and start up when you're ready. Okay, this first one, we look at sodium first. Sodium has a mass of 22.99, and then bromine has a mass of 79.90, and so we're just going to add those two numbers. And if we do that, we get the number 102.89, and then can't forget our unit of grams per mole. Okay, and then for our sig figs again, we're adding, so we're going 2 after the decimal, which is what our answer did. So I'm going to actually write that over here. Okay, and then I'm going to erase this so we have a little bit more space for our next problem. Okay, this next one's a little more tricky because it's got a polyatomic ion in it, but really that doesn't affect anything. We don't know the mass of just polyatomic ions, so we're just going to break it apart when we are calculating this. So we're going to take the mass of the lead, which is 207.2, plus the mass of our sulfur, which is 32.07, plus we have 4 oxygen, so we're going to multiply 4 times our oxygen, which is 16. And make sure if you're using a calculator for this that you are using parentheses for your multiplication. So this one you should get 303.27 grams per mole. However, this one, if you notice, we're adding again, so we're using the decimal place rule. Only goes 1 after the decimal place. So that means our answer is going to be 303.3 grams per mole. Will be our actual answer over here. Okay, and we will do some more of these, but this calculating molar mass, we will use this in the future for when we are doing more unit conversions with moles. So if you missed class, there is a ticket out the door. It's just one question. Make sure you're calculating the molar mass of NaCl and make sure that you include the units. You can turn that in next time.